What's up, guys? This is the Round Bottom Flask, and welcome to the part 4 of our lecture series on the concepts of structure and bonding in the context of organic chemistry.
So in this video, I will discuss the theories on how covalent bonds are formed. So there were two theories, or rather there are two theories on how covalent bonds are formed. The first one will be Valence Bond Theory. So according to the Valence Bond Theory, a bond is formed when there is an effective overlap between the valence atomic orbitals of the two atoms. And the electrons in the valence orbitals that when they overlap become bonding electrons, and they are only located at the area where the overlap has occurred. So if you can see in our illustration here that when the atomic orbitals of two hydrogen atoms here to form the hydrogen molecule, the overlap is just here. And if you see, the bonding electrons also reside in that overlap. They don't roam around the atoms involved in the bond. So in order for this bond to occur, we have already seen that in a covalent bond, each atom involved in a covalent bond should share one electron. So in order for that covalent bond to form, the valence orbitals involved in the bond formation should be half-filled. Okay, so for example, here in hydrogen sulfide, hydrogen atoms only has one electron, so their 1s orbital is already half-filled. While in the sulfur atom, their valence 3p orbitals, two of them are half-filled, and they are the ones that will interact with the 1s of the hydrogen atoms to form your hydrogen sulfide molecule, while the lone pair, or rather one of the lone pairs will reside on the 3s and on the filled 3 and on one of the filled 3p orbitals. So let's have a look on how valence bonds are actually formed. So if you can see in the interaction diagram, there are actually we have noted 4 points here during bond formation. So at the first point here, the two hydrogen atoms here are too far apart, so there is actually no interaction. There is no interaction whatsoever between these two atoms. Thus, since there is no interaction, the energy is 0. As the atom approaches, as in state 2, there will be attractive forces. So the attractive forces will be between the nucleus of one hydrogen atom and the electrons of the other hydrogen atom, and vice versa. So they will pull each other together until they reach an optimum distance, wherein there is a balance between attraction and the repulsion. Now, this optimum distance between the two hydrogen nuclei is what we call as the bond length, and the energy associated with this optimum distance is what we call as the bond energy. Drawing the two hydrogen atoms too close to each other, will lead to a domination of the repulsive forces and will dramatically increase the energy of that state. So there are two types, in the context of organic chemistry, there are two types of bonds that are formed according to the valence bond theory. One is we have as the sigma bond. So this is the one that that I've shown you here in both on the bonding of hydrogen sulfide and also on the bonding of two hydrogen atoms to form your hydrogen molecule. These are formed due to a head-on overlap between atomic orbitals. So that means there will be what we call as a head-on collision between two atomic orbitals, and that will lead to a formation of a sigma bond. And as we can see, the sigma bond here is cylindrically symmetrical. So that means if you cut a cross section of the sigma bond along the sigma bond, or rather across the sigma bond, you will see that the cross section is a perfect circle. So that we mean that what is meant when we say as cylindrically symmetrical. Another is a pi bond. Pi bond is formed due to the sideways overlap between coplanar atomic orbitals. So that means the atomic orbitals should lie on the same plane. This is usually observed between the overlap of two p orbitals, or between an overlap between a p and a d orbital. So they are significantly weaker in terms of they're relatively weaker than sigma bonds, and thus are easier to break. Now, another consideration here is, I forgot to tell you this, is that p orbitals actually has a phase, which is the result of solving the Schrodinger's equation. So if you notice that p orbitals lie on a certain axis, right? So that axis. So if this is the origin of that axis, if this is the origin of that axis, oops, it's not visible. I'll change the color of my pen. So I'll make it, yeah, I think this color is perfect. So let's say this is the axis of this p orbital. Let's say this is a py orbital. This is a p, oops, it's not visible again. So this is a py orbital. Obviously, this other orbital here will also be a py. Okay, so if you notice, it lies along the y-axis, while the origin of that y-axis will be the node, or the area of zero probability of finding the electron. Now, if you notice in the Cartesian plane, we have a positive. Every axis will have a positive and a negative side. So let's say this is a positive y and this is a negative y. Okay. Now there is a notation there that the ones lying on the positive axis will have a notation of a positive sign, and the one lying on the negative axis will be on a negative sign. So we'll have a negative sign. So this is again a result of solving the Schrodinger's equation. When you solve the Schrodinger's equation, and there are two, when you solve the Schrodinger's equation, it will result to the same value but with a positive sign, and it will result to a different the same value but with a different sign. So this is the result why there are why the p orbital has a positive and a negative sign. So this is not only applicable to p but also on d and the f orbitals. Now, in order for a pi bond to form, the signs should be what we call as in phase with each other. When we say in phase, that means the positive sign should make a sideways overlap with the positive sign of another p orbital, with a positive side rather of another p orbital, while the negative side will overlap with the negative side of the other p of that same p orbital. Because so in order for a pi bond to be formed, because if the signs were different, so if a positive sign will overlap with a negative sign and vice versa, they will cancel each other out, and thus no pi bond will be formed. So, and that sign is also inherited by the pi bond. So this will be, if this is our positive side of the p orbital, so when they do a pi overlap, this will be the positive side and this will be the negative side. So we need to take note of that because it will be important to know whether a pi bond will be formed or not. Okay. So we have, let's have methane. So we have, this is the orbital diagram for carbon, right? Now, according to the valence bond theory, in order for the carbon to form CH bond, in order for carbon to form CH bonds, as in methane, this what they call this? This electron here, one of the electrons in the 2s, will be promoted to the 2p in order for us to have 4 half-filled orbitals in order that will interact with hydrogen atoms to form your your 4 CH bonds as in methane. Okay, so that means since 2s is closer in the nucleus than 2p, and they also have it also has a different shape than 2p, that means not all of the CH bonds will have an equal length in methane. However, as you can see in methane, all of them have the same length and the same bond angle, which is 109 picometers in terms of bond length. So that means the CH bonds in methane are equally the same, even though valence bond theory dictates them. A simple valence bond theory dictates otherwise. So what is the reason behind that? So in 1931, Linus Pauling proposed a concept called hybridization, wherein orbitals on the same energy level mix in order to form new orbitals of the same shape and of the same energy. That means they are degenerate orbitals. So let's go back to methane. So in methane, in order for methane to form that 4 equidistant CH bonds, what carbon did was one of the s orbitals combined with one of its 2s orbitals rather, mixed, hybridized with all of its 2p orbitals to form your sp3 orbitals. So if you notice, the sp3 orbitals here has a small node here. So this is because they inherited this node from the p orbitals, okay? But there, if you notice, the one node is larger than the other because of the s orbital. Remember that the s orbital is spherical in shape. It has is spherical in shape. So what happened here? It inherited some of the properties of the s orbital, and it inherited some of the properties of the p orbital, particularly the part where they have a node and a lobe, and a small lobe. So if you combine them, they will have the sp3 hybrid orbitals in carbon would look like. Now the question here is, since they will have lobes, which is the positive side and which is the negative side? Now by convention, the positive side will be the larger lobe, while the negative side, the one with the negative sign, will be the one with the smaller lobe. Oops. Okay. Now, how double bonds are formed naman? Now, in a double bond, not all of the p orbitals are hybridized. Instead, only 2 p orbitals hybridized with the s to form your sp2 hybrid orbitals. Now, let's take for example an ethylene, the ethylene molecule. Now, the 2 carbon atoms in ethylene are sp2 hybridized. So what happens here is that the sp2 hybrid orbitals from each carbon atom will form a sigma bond, while the unhybridized p orbital, which is half filled, is the one what will do the sideways or overlap to form the pi bond. Now, this is not only applicable to those who will form a double bond, but is also applicable to molecules that adapt a trigonal planar geometry. So one example here is borane, wherein the boron is sp2 hybridized, wherein it forms a sigma bond with each of the hydrogen atoms. The p orbital will be jutting out here, in front of us, jutting forward and backward of the plane of the paper, and if you see the Lewis structure, there are no lone pairs. That means the p orbital, the unhybridized p orbital there, will be vacant. Now, in triple bonds, only one p orbital will hybridize with s orbital to form sp orbitals. So just like in sp2, the 2 sp orbitals will one sp orbital from each atom will form a sigma bond, while the 2 unhybridized p orbitals will form a pi bond. And this is also applicable to all molecules with linear geometry. So for example, your beryllium difluoride, your beryllium here will be sp2 hybridized, which will form a sigma overlap with the fluorine atoms, while the other 2 unhybridized p orbitals of beryllium will be vacant. So there are several rules that we need to follow when we're performing hybridization of atomic orbitals. So again, hybridization will result to a new set of degenerate hybrid orbitals. Next is, since Linus Pauling proposed that hybridization only occurs on the same value of n of atomic orbitals, that means hybridization can only occur on orbitals of the same energy level. So also we follow the rules of what they call this, of conservation of atomic orbitals. That means number of hybrid orbitals formed is equals to the number of atomic orbitals involved in hybridization. So let's have an example here for the hybridization of carbon atom in methane. So when it hybridizes, the 2s and the 2p here diminishes, which eventually form sp3 orbitals of the same energy. And if you notice, the energy here is quite a midway between the energy of that of a 2s and of a 2p. So the valence bond theory can also explain the presence of resonance. So in resonance molecules, what happens there is that adjacent pi bonds, or 2 coplanar p orbitals, or coplanar pi bonds will fuse with each other to form a conjugated system, wherein that electrons are delocalized all over the system. If you look at the benzene, so the benzene molecule has 3 pi bonds. That means it has 2, 4, 6 p orbitals overall. And if you notice, benzene is a planar molecule. That means all of its p orbitals here are coplanar with each other. And if you notice, since they are coplanar with each other, they can fuse to form that resonance, that conjugated pi system. And the electrons residing in that pi bond, in that previously isolated pi bonds, will now be evenly distributed all over the conjugated pi system, which further lowers the energy of the molecule and stabilizing it. Thus, and that results to resonance structure. So actually, the resonance here in this case is or in most cases, in almost all cases rather, is a consequence of electron delocalization all over the pi conjugated system. Now, elements in the period 3 of the periodic table can achieve hypervalency. It's because they have access to their vacant d orbitals of the same n. So, for example, here in phosphorus pentachloride, it can go beyond the octet. Phosphorus rather can go beyond the octet. It's because it can access its vacant 3d orbitals involved in hybridization. So if you see here in phosphorus pentachloride, in order for it to form five covalent bonds of equal lengths, it needs to form 5 hybrid orbitals. So it already has 1 from 3s, 3 from 3p, it only lacks 1. So in order for that to happen, it will get 1 vacant orbital from the 3d and involve it in hybridization to form the sp3d hybrid orbitals. So remember that the subscript here, the superscript rather, here indicates how many of this orbital was involved in a hybridization. So since the superscript of p is 3, that means 3 hybrid orbitals, 3p orbitals were involved in the hybridization. While since s and d has no superscript, that it is assumed that their superscript is 1, and therefore only 1 of their orbitals were involved in hybridization. So let's have a look with an octahedral molecule such as sulfur hexafluoride. So in order to form 6 covalent bonds of equal bond length, what will happen is that sulfur will need to form 6 degenerate orbitals. So it will now access, instead of 1 but 2 hybrid orbitals, or rather 2d orbitals, to form your sp3d2 orbitals that will bond with fluorine to form your sulfur hexafluoride. So that's the end of my lecture video. So if you find this video educational or interesting, please like this video and don't forget to subscribe to our YouTube channel. Once again, this is the Round Bottom Flask signing off. See you guys